Hey guys, my name is Uday, and in this video, for the next few minutes, we'll see the concept of phase delay and group delay. Now, before we go into phase delay and group delay, first let's have a look at the Fourier transform of a signal. So the formula is right there, which we all know. Quite clearly, this Fourier transform is a complex function which has a real and an imaginary part. Now, this complex function can also be represented as magnitude and argument. So we have written capital X as mod of capital X into exponential of j5, where mod of capital X is the magnitude and phi is the phase. Now the square of the magnitude actually gives you the energy density of the spectrum. So what actually this magnitude and phase of the Fourier transform signify? We can consider Fourier transform as representation of the signal by exponential components with different frequencies. Now, the magnitude of the Fourier transform gives you an idea of amplitudes of these components, whereas the phase gives the relative phases between these components. Example, if for example consider a signal x of t, and if its Fourier transform is capital X of j omega. Now if its magnitude is 0 outside a small band centered at some particular omega 0, so if the Fourier transform is confined within a smaller gap of around 0, then the signal will display only low frequency oscillations. Whereas if you want to know the importance of phase, look at this. Consider capital X of j omega and capital X of minus j omega. They have same magnitude, but they have different phases. If you take the inverse Fourier transform of these, then you get x of minus t and x of t. These two are completely different signals. So this signifies the importance of phase. Now let's look at a practical example of why phase is important. In this slide, take a look at the picture from the top left corner. So this is an image taken, and now you are taking the Fourier transform of this image, and the second picture from the top is its magnitude, and the first picture from the bottom is its phase. Now do one thing, take the magnitude, set the phase equal to 0, and take its inverse Fourier transform. You get uh, second picture from the bottom. This is nothing like the original picture. Whereas now if you set magnitude equals to 1 and take the phase as it is, you get third picture from the top. This looks a lot like the first picture. I mean, at least it has some resemblance. Now what else we are doing is we are taking the phase from the first picture, we are taking magnitude from the first picture, and yeah, we are taking phase of the first picture and we are taking the magnitude of the picture that is at the bottom right corner. Now this on inverse Fourier transform will give you the picture, the last picture from the top. Now let's look at the magnitude phase representation of the frequency response of linear time invariant systems. So a linear time invariant system is characterized by this equation. This is convolution theorem, as we all know. So if an input signal is x of t and h of t is the frequency response of the system, if it's a linear time invariant system, then we get output as y of t. Now if you take the Fourier transform of this, capital Y, if capital Y is the Fourier transform of y, capital H is the Fourier transform of h, and capital X is the Fourier transform of x. This is nothing but direct multiplication. Now the magnitude and phase of the output are denoted differently. If you take a look at the magnitude, it's direct multiplication of capital H and capital X. Whereas if you take the arguments, you have to add the argument of capital X and capital H. So as we have seen, the magnitude of the input Fourier transform is actually scaled by passing through an LTI system. That is, it's multiplied by capital H. That is, the magnitude of capital H of j omega is called the gain of the system. Whereas if you take the phase, it's rather shifted, it's added rather shifted, so it's called phase shift of the system. The argument of the frequency response of the system is called the phase shift of the system. Now let's get into the topic. So linear phase, there are two types of phases, linear phase and non-linear phase. So in linear phase, the phase shift which we have seen earlier is a linear function of omega. Now in this case, the situation is pretty simple. For example, consider the Fourier transform, consider some LTI system whose Fourier transform is this, e power minus j omega t naught. Now, this has a magnitude of 1, whereas it has a phase of minus omega t naught. So, if you take, if you apply the equations and get the output, you get the output as just a shift in time domain. That is, if you take x of t as an input, then you get x of t minus t naught as an output. So, this is nothing but a change or a shift in the time domain, but the shape of the pulse remains the same. So take a look at that picture. That was the input signal and the right one is the output signal. The shape of the signal has not changed, but it was shifted. It shifted for about some change, and this can be easily calculated by this formula, that is minus argument of capital H upon omega. I'm going to verify this for you. In the previous example, as we have seen, the phase was minus omega t naught and the shift was t naught. So put those values in here. So minus of minus omega t naught upon omega, that gives you t naught, and that's exactly the shift, and this shift in time is called the phase delay. Now there are a lot of cases where this phase shift is not a linear function of omega, then it's non-linear phase, and then things can be a little different. In this case, the relative phases of complex, as we have said earlier, Fourier transform is a summation of exponential components of different frequencies. In case of nonlinear frequencies, the relative phases between these components are shifted, and they are not shifted in a particular manner. And now when these components are superimposed, and then when you try for the original signal, the result completely differs from the original signal. As you can see in the figure, the shape now has completely changed. It doesn't look anything like the original signal. Let's apply the concepts of time delay which we have seen in linear phase to nonlinear phase characteristics. Here the delay is different for different frequencies. So let's take a small narrow band for our study. That is, the Fourier transform is 0 outside a small band whose center is at some omega equals to omega naught. In this small band where the frequency does not change a lot, we can approximate the phase to linear, and this linear approximation gives you the phase as minus pi minus omega alpha. Now the output of the Fourier transform of the output becomes capital Y of j omega, which is shown there, and from that equation the magnitude is not only scaled by mod of h, but there is an additional factor of e power minus j phi. But look at the delay part, it's minus j omega alpha. So this is a delay for all the frequencies around omega naught. So this small band of frequencies have a common delay of alpha. This delay is otherwise known as group delay, as it is common for all the frequencies around omega equals to omega naught. So group velocity, now we define group delay as the equation written at the bottom. This is group delay. It depends on the frequency. It is different for different individual frequency. Now in this picture, that's the input signal at the top and the output signal is at the bottom. Here the group delay is 20 and the time delay is 10 seconds. You can observe it here. A group is shifted by 20 units, whereas a particular signal in the beginning is shifted by 10. So the references for this presentation have been taken from OpenHead Signals and Systems textbook and a lecture on digital signal processing from University of Washington. Thank you.